Hi, scholars. We're going to do a couple of problems that use the idea of percent change. And just as a quick review, we have this formula that allows us to calculate percent change. And it's basically, it's new minus initial over initial. And this new minus initial is really just talking about what changed, right? If you find the difference between what something was and what it is now, this is, in fact, what changed. And the big idea with percent change is we're comparing what changed in comparison to what we started with, right? And that's really the key idea for this whole day today. And I just want to call your attention that in this formula, there is one value that is the new value. There is another value that is the initial value, right? And that's above and below. And then there's another value that is the percent change, right? So these are the three values that we have. So notice, with this kind of an idea, this kind of formula, if you give me any two of these three things, I can find out the third, right? It's just algebra. It's just some arithmetic to find out the third. Okay, so let's take a look at an example. Xavier usually earns $40.85 per hour working as a high school math teacher. So this is his initial salary. He just found out that he is going to get a 4% raise. So this is the percent change, his percent increase, 4% over and above his $40.85 salary. He's going to get a 4% raise since his students really understand fractions. Whoa, that's amazing. It is very hard to really understand fractions. He must be a really good math teacher. Okay, so let's call his new salary x. This is what we're trying to find, and we can use this formula, right? We can write x minus his initial salary is $40.85, $40.85 all over $40.85 equals his percent change is 4%. Now I can't just write 4%, right? Because I have to turn it into a number, a decimal we can actually work with. So I can write that as 0.04, right? 0.04, we could even say 0.04. And then what can I do? Well, I could cross multiply. I could basically multiply. It's essentially the same as multiplying both sides by 40.85, right? On the top and the bottom, okay? Kind of like this. These ones cancel. We got our x minus 40.85 equals 0.04 times 40.85. Oh, look at all this work. We can, of course, add our 40.85 to both sides of the equation. And I'm going to write this as I'm going to add one of these things, right? I'm going to add one of the 40.85. And I end up that x equals, well, it's going to be 0.04 times this amount plus 1 times this amount. It's the same thing as 1.04, right? So in other words, what we're really doing here is we're adding the 0.04 plus the 1, and that's becoming 1.04 of this original salary, okay? And we can do that, find that in our calculator. So I can go 1.04 times 40.85. I press my enter, and $42.48. So his new salary is $42.48 roughly. Okay, so we can write x equals $42.48. Now, notice that I did use this formula, right? But I could have gotten the answer much easier. I could have said, he's going to get a 4% raise. That means on top of his 100% that he has 100% of that, he's going to get a 4% raise, right? Okay, so this is the amount that his salary is changing, right? And so I could have immediately just done that calculation in one step, and I would have gotten to the same answer, okay? So this formula, you can always use it, right? But sometimes they're going to be shortcuts. They're going to be easier ways to sort of get the answer. Now here, I need to be able to interpret 4% raise as 1.04, right? This is the important part of this question. Okay, let's take a look at another example. So another example, Danavia is buying a pre-calculus textbook online. There's a sale, and the book is 35% off of the original price, P. So it cost P, and it's 35% off. The sale price after that 35% off is $52. And we can ask ourselves, what is the original price? Now again, we could, if we wanted to, use the formula, right? This is 35% off is a percent change. And we would actually, if we wanted to put this in the formula here, right, this would actually be minus 0.35, right, in the calculations. And the sale price is $52. So that's the new price, right? So that would be our new price. And the question is, what is the original price, P? What was the initial price, P, right? So this is how, if we wanted to use our formula, we could do it. But boy, that's going to be complicated, okay? So instead, we're going to actually take all this information and we're going to turn it into one algebraic equation, okay? So let's talk through it. There was an original price that we don't know what it is. There is what it used to cost. And then something happened to it. We took 35% off of it, okay? Well, how can I represent taking 35% off? It's as if I had 100% of the price, and then I took 35% off. So how much is on, right? How much is left over after I took off my 35%? 100 minus 35. So in other words, 65% is left. 65% of the original price is left, okay? Well, how can I represent 65% of P? Well, 0.65 times P, right? We know how to move a percent into a decimal. That's what we did last week. And so this is how I can represent 35% off. So this thing all represents 35% off. And if I didn't want to work with decimals, I could have immediately just worked with percentages. I could have immediately just worked with decimals, because this 100 minus 35% is equivalent to 1 minus 0.35, which is 0.65, which is exactly what we have here, okay? So this is what we have. We have 0.65 of P, okay. That's the sale, and the sale price is in math. When you see the word is, we say that that's equals, and it equals $52. Great. So if this right here is my equation, right, I can solve it. Divide both sides by 0.65. Divided by 0.65. You say, wait a minute, can I divide by a decimal? Yeah, sure, you can. It's a number, right? You can divide by any numbers you want. So let's take a look. I can clear this, and I can go 52 divided by 0.65. Press enter. $80. So the original price, so this means that the original price P, our original price P, is $80, okay? So that's the answer. And we can check this. Say, well, let's imagine it was $80 and I took 65%, or if I took 35% off, right? That would be 65% of the original price. And if I do 80 times 0.65, of course I'm going to get to the sale price of $52, right? Division and multiplication, the one thing undoes the other thing. Okay, let's take a look at one more example. Fatu has a square. She decreases the length of the square by 40%, okay, and increases the width of the square by X%, okay. And so now she has a rectangle, right? If you take a square and you smush one side, pull out the other side, it's a rectangle, okay. If the area of the original square and the new rectangle are the same, so they have the same area, okay, then what is the value of X? Okay, so let's model, first off, a decrease of 40% for the length. Well, we know how to do that. We can do 1 minus 0.4. It used to be 100% of the length, and now it is, right, if we let L equal length, now it is 1 minus 40%. Sorry, that's a 1 there. That's a 1 minus 40%, and so that's really 0.6, right? That's 60% of the original length is left, right? It got shorter, okay? And now the question is, how are we going to model increasing the width by X%? Well, in a similar way, if the original width was W, and we're increasing it now, I can do 1, start with my 100%, plus, I don't know how much, x, right? Now this x is going to be slightly different from here because this x represents a decimal, and this x is, we actually want a percentage, but let's just use the same letter here because otherwise it just gets a little too confusing. So basically we have a situation where I have 0.6 and of the length, right? And if I want to find the area, of course the area is nothing more than length times width. And so the area of the rectangle is 0.6 of the original length times 1 plus x, okay, of the original width, that's the increase of x%, okay, and all of this, I want it to be the same as the original square. So I want that to all be the same as the original square, which was the original length times the original width. Okay, and now this is really nice because that original, right, just to be totally clear, this is the area of the square, right? So this is the area of the square, this is the area of the rectangle, and we want those two things to be equal to each other. Okay, so let's get rid of those boxes. So immediately, there's a length there and a length there, right? I can cancel them. There's a width there and a width there. I can cancel them. So immediately, I can get this equation. It's just 0.6 times 1 plus x equals, and when I cancel out the lengths and I cancel out the widths, I end up with just the number 1, right? If I divide both sides by L and divide both sides by W. I can do that because we're just multiplying all these things together. And now, how the heck do I solve this? Well, you're going to solve this in the same way you solve an equation that looks like 2x equals 6. And you say, okay, let me divide by 2, right? Okay, it's the same thing, only here we're going to divide by 0.6, right? We're going to unpack this 0.6. Let's divide by 0.6. Let's divide by 0.6. And we're going to get that 1 plus x equals 1 divided by 0.6. Let's go to the calculator, right? 1 divided by 0.6. Enter. 1.66666. That's fine. Let's call it about, let's call it about 1.67. That's okay. Roughly, right? We can estimate. 1.67 is equal to 1 plus x, well then, we can conclude that x is something like 0.67, right? So we want that to increase the width by x%, right? So as a percent, our final value is x is 67%, okay? 67%. And that's what I said, what I meant earlier when I said that this is, we're going to have to, when we get this thing as a decimal, we're going to have to convert it back into a percent here. So 67% increase. So that's kind of strange. You would think that if you decrease the length of the square by 40, you should increase the width by 40, plus 40, minus 40, right? But in fact, it turns out you would have to increase the width by 67%.